This is in section 3, and this is about sampling distributions and confidence intervals. And what we have is the central limit theorem. And this is what allows us to make bets in statistics, bets on the average in particular. If we have a normal distribution with a mean of 100 and a standard deviation of 15, then our bets are that 68% of the individuals from this population will be between 85 and 115. And 70, 2 down, 2 up, 130. 95% of the individuals in that population are between those two limits. All the bets are made in increments of standard deviations. For simplification, 2 up, 2 down is 95%. 1 up, 1 down is 68%. Bets on individuals are lousy. They're terrible. This is why the car insurance company doesn't bet on you as an individual. They bet on you as a member of a group. But they're betting that the people in the group, on the average, will do what they expect. All the bets that we make that are any good are bets on the average. This is a lousy bet, and we can't improve it. What we want to bet on is averages. And that's where the central limit theorem comes in. Basically, the central limit theorem says two things. The first one is that we can use normal distribution bets to bet on the average, no matter what the original distribution looks like. The second thing is, bigger sample sizes are better than small sample sizes. Because when we make a bet on an average, we are betting on the average of averages. We're betting on the average of thousands of possible samples. Go into Canvas. We need Canvas here because we've got two files there we're going to download. And when you get into Canvas, there's Files on the left-hand side. Click on Files. And there's two files that we're going to use. One is called 1 to 9 sample means. And the other is Central Limit Theorem Demo. There are a lot of central limit theorem demonstrations online. If you search on central limit theorem demonstrations, you'll get a whole bunch of stuff. Khan Academy has got a really nice explanation of the central limit theorem. This is how we can make bets on an average. This has a normal distribution with a mean of 100 and a sample standard deviation, a standard deviation of 15. There's a uniform distribution. This is a flat line between 70 and 130. The average is 100 and the standard deviation is 17.32. There's a skewed right distribution. And there's a skewed left distribution. Over on the side, beside each one, is the result of 100 individual sample means. The distribution of 100 individual sample means from the skew left distribution. And this is sample means. And the distribution of sample means is normal, regardless of what the original distribution looks like. Here's a skewed right distribution. And the distribution of sample means, 100 sample means, from the skewed right distribution. This one is the uniform, and this is the normal. And right now, all of these are from a sample size of 30. But the point is, no matter what the original distribution looks like, the distribution of possible sample means from that distribution will be normal. That means we can use normal distribution probabilities. We can bet on 2 standard deviations up and down, 1 standard deviation up and down, or whatever number of standard deviations. But we can treat the distribution of sample means as though it were normal. Not only that, but it is a much tighter normal distribution than the original. This one, the distribution from normal, has a mean of 100, standard deviation of 15. In the distribution of sample means, the mean is going to be the same. And there may be one over here, some numbers. This is the distribution of 100 sample means of samples of size 30. So I took 30 observations, averaged them. Then I took 30 observations again and averaged them. And did that 100 times. The average of the averages is pretty much the population average. So the average of the sample averages estimates the population average, and it does it pretty well. For this one, we got 101, and the average from the population is 100. This one, the average from 100 samples is 99.4. This one has an average, the skewed right, of 72.8, and the average of the average is 72.8. So that these things that we're betting on, we can use normal distribution probabilities. We can use 2 standard deviations up and down, 1 standard deviation up and down. And here's the kick. If I really wanted to do this with the official rules, I would need to do 1,000 or 2,000 samples, not just 100. We're betting on the average of thousands of samples. We only get to do 1 sample. And the bet is that our 1 sample is as good as thousands of samples. That, to me, was always an astounding bet to make. But that's the bet we get to make. For the rest of this recording on the central limit theorem, there will be 2 files downloaded from Canvas: central limit theorem demo and 1 to 9 sample means and standard errors. Both of these are macro-enabled Excel files, and they may not run once they are downloaded because they are restricted. To get the files, go into Canvas, click on one of the files. Here I'm going to choose Central Limit Theorem Demo, and then download that file. The file is downloaded. Then go to whatever directory contains your download files. In mine, it is in Downloads, and right-click on the name of the file and go to Properties. In the Properties box at the bottom is Security. Click on Unblock. Okay, then you can open the file and then enable content, and then you can choose the distribution name and the number of samples, and this is used in the recording for the central limit theorem demo. Let's go back to the central limit theorem demo file and make sure normal is highlighted, and then go to a sample size of 10. If we do 10 observations, 100 samples of 10 observations each, we get the same shape basically, but it will be wider. It will be more dispersed. So if you go down, there's a run button. And we get a cluster still, but it's wider. It's more dispersed. If you go to 50 and run, it becomes tighter together. Right. More samples are better. The sample size is the only control we have in statistics. Right. Look at the sheet. On the on the top left, there is a sigma over the square root of n. This is called the standard error of the mean. This is actually the standard deviation from the sample means, the population of sample means. Sample size will reduce the spread, the uncertainty. And the bigger the sample is, the smaller that number becomes. So for the first one, we have a normal distribution with a standard deviation of 15. If you divide 15 by the square root of 10, 15, 10 square root, divide 4.74. With samples of size 10, instead of having 100 in the middle and 15 out, one standard deviation out, and 30 for 2 standard deviations out, we have 1 times 4.74, 100 plus 4.74, and 100 minus 4.74 for a 68% bet on the average. If we go out 2, we're still at, that's like 5, 100 to 110, and 100 to 90 for a 95% bet, instead of the 15 and the 30. For the sample size of 20, we have 20 divided by the square root, divided by the square root of 20, which is 3.35. 20 makes a better bet than 10 because the standard error, it's called the standard error, and it's written different ways. S sub x bar is one of them. Instead of just S for standard deviation, the standard deviation of sample means is called the standard error, to make a distinction between that and the standard deviation. The bigger the sample size, the smaller the standard error becomes. So for 30, 2.739. And the decimals are pretty arbitrary. 50 samples, 2.121. The more samples we get, the better our bet on the average becomes. And if you look back at the Excel file, over on the side is the average and the standard error. For this, the sample size was 50. So that our theoretical value was 2.121. The actual value from all the samples that we did is 2.15. So it works out. The more samples you have, the smaller the standard error is, and the narrower are the limits on the bet. And we're still doing normal distributions. 68%, one standard error up and down. 95%, two standard errors up and down. For the uniform distribution, the standard deviation of the population is 17.32. If we do the same thing, and divide by the sample size, square root, we will get the estimate of the standard deviation of the sample means, called the standard error. And each one of these gets smaller. Uniform distribution is just flat. The result of doing continued samples has a normal distribution with this standard error. 17.32, 10, square root, divide, 5.47. 17.32, square root of 20, 3.87. 17.32, square root of 30, 3.16. 17.32, square root of 50 is 2.45. If we go back to the Excel file, now we're in the uniform distribution. Here is a sample of size 50. Make sure that the uniform distribution is selected and run, and you can see that for this particular sample, the standard error is 2.59, and it's theoretically 2.45. So we can make a bet on the average from that distribution of 100, whatever the average is, plus and minus 2.45. And plus and minus 2 times 2.45 for 68 and 95% bets. Also, we can make any bet we want. We can make an 83.2% bet. We just need to look up the probability, the number of standard deviations in the standard normal table. 68% and 95 are Actually, 95% bet. It's the only bet that most people ever make. I worked for basically 50 years, and nobody ever wanted anything but a 95% bet. Because not because that's a standard, it's because the guy who developed this, that's the example he used. And it's been that way ever since. So somebody says, what confidence interval do you want? What bet do you want? Say 95%. And everybody would go, okay. If you said 82%, they'd look at you like you were crazy. In all of these, no matter what I begin with, I get a distribution of sample means. Here I have 100 samples, individual samples, with the averages all made into a distribution. The central limit theorem says basically that if I did an infinite number of samples of a particular size, I would get the standard error estimate. We only get to do one. So we are taking a lot on faith, but that's the way statistics works. Also, we go to the other file. This is the mean, standard deviation, and standard error for samples of 20, 50, 100, and 1,000. Instead of a picture, because a 1,000 would be hard to get, look at what the averages are. And this is from a uniform distribution of numbers 1 through 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. The average is 5. Here's our samples of 20, 50, 100, and 1,000. Look at the average. What happens to the average for each of those things? Is it different? A little bit. It's about 5, 5.1, 5.15, 5.026. Click on the button and let it run again. And we get basically 5 for the average. And no matter what sample size we have, 20, 50, 100, or 1,000, or if I put in 20,000, I would get about the same average. The average doesn't change because my sample averages estimate the population average. Look at the standard deviation. Is there a big difference between samples of size 20, 50, 100, and 1,000? And no matter how many times you do that, the order changes a little bit. It goes up and down, but the standard deviation is basically the same. No matter how many samples I take, or what the sample size is, the average is going to be pretty much the same. The standard deviation is pretty much the same. That means that my bet on an individual doesn't change no matter how big the sample size. The standard error is what changes. This is the only control you have in statistics, is sample size. So that for the samples of size 20, I have a bet of about 0.6 up and down, one standard error up and down for 68%, two standard errors up and down for 95%. If I have samples of size 50, my bet improves. Samples of size 100, the bet improves. If I go to 1,000, I have an average of 5 plus and minus 0.08 for 68%, and plus and minus 1.6 or 0.16 with the samples of size 1,000. The more samples I have, the better, because it makes a better bet on averages. Bets on averages are the only thing that are worth making. This is why if you're playing a card game, go to a casino and you're playing craps, you are betting on an individual event. What is the house betting on? The average. They're betting on everybody that plays that game. And that's the difference between their bet and yours. You have a lousy bet. Their bet is so good that they aren't going out of business. The larger samples make better bets because we're using the standard error. And no matter how many times we do this, the average from each one goes up and goes down, but it's basically the same. The standard deviation from each one goes up and goes down, but it's basically the same. Only the standard error of the mean, that's the standard deviation from a huge population of sample means. That's the bet in statistics. We're betting on the average. And we're betting on the average of thousands of averages. Except we only get to do it once. The second part, go to the next page. This is what we gain with sample size. The divisor in these things is the square root of the sample size. Square root of 50, square root of 30, square root of 20. If we double the sample size, we don't get twice as much information. Each sample we take contributes less, so that this is the gain we get with sample size. Suppose our first sample cost $1. It gives us $1's worth of information, 1 over the square root of 1. The second sample cost the same, $1. Now we're $2 in, but that second sample only gives us about 70% of the information that the first sample gave us, 1 over the square root of 2. The third sample still cost $1. The sample cost doesn't go down. It just keeps accumulating, and each sample we get contributes less to our information. So that when we have that divisor of a square root, 50 is not 50 times better than 1. It's only 1 over the square root of 50. From 1 to 25, the first sample gives us $1's worth of information, and we paid $1 for it. At 25 samples, we've paid $25, and we only get 20% of the information that we did with the first one. Every sample costs as much and gives less and less in terms of information. Look at the graph. Look at the sample size of 30. What happens past 30 in terms of the information that we gain? It still decreases, but it doesn't decrease as fast. 30 in statistics is a large sample size, no matter what you're doing, because past 30, you are getting less and less and less and less information for every sample you get. So for 1,000, if I could put it on this graph, it would be lower than 30, but it would be not much lower than 30. I get more information gained from 25 to 30 than I get from 995 to 1,000. This is the central limit theorem. This is how we get our bets. we can use standard normal, that is, measurements of standard error for our bets. How many standard errors up and down, and an increased sample size always gets us more, but it gets us less and less and less information.